So we saw, though, that translations happen when we're adding or subtracting. If you see addition or subtraction, think translation. Right? If you see something being multiplied by a negative, think reflection. When you see something being multiplied by another number, okay, not a negative, but a number, think stretching and shrinking, okay? Then it's just a matter of figuring out exactly how it was stretched or shrunk, and that's what we'll look at here, okay? We've been talking about the parent function x cubed, so let's look at horizontally and vertically here. As it was with shifting, the horizontal stretching and shrinking is the one that behaves kind of the opposite of what we would expect. Okay? Typically you expect that when you multiply something by a larger number, it's going to get bigger. And when you multiplied it by, say, a fraction, it would get smaller. But with horizontals, this works a little bit, this works in reverse. Okay? The bigger the number you multiply x by, the narrower, the smaller the graph is going to get. It's going to be shrunken horizontally. Okay? So, for example, if we had f of 3x, okay, and in our function we were dealing with x cubed, all right? If we had 3x cubed, that would only be a third as wide as our original parent function. Okay? Again, it's an indirect relationship. So 1/3 as wide. Okay? If I wanted to make it 3 times as wide, what would I multiply the x by? A 1/3. Okay? So if I had f of 1/3 x, 1/3 x quantity cubed, that's going to make it 3 times as wide. Okay? Now, the vertical, on the other hand, the vertical stretch or shrink is a direct relationship. It's exactly what you would think would happen. When you multiply by a larger number, it's going to get stretched, it's going to get taller. When you multiply it by a fraction, it's going to get shorter. Okay? So, in this case, if we had, notice we're multiplying the actual function by a value. So we would have, say, 3 times f of x, which would look like this with our parent function x cubed. It would just be 3x cubed. See the importance of parentheses here and knowing your order of operations. Only the x is being cubed. So 3 is creating a vertical stretch, and it's going to be 3 times as tall. Or you could think of it in terms of each point. Each point will have its y coordinate multiplied by 3. Okay? The end result is, again, 3 times as tall. Okay? If we had a 1/3, a fraction, and it was something like 1/3 times x cubed, that would then be shrunk. It would be compressed vertically. So that would only be 1/3 as tall. Okay? Alright, so any questions about this before we just work through some examples? Okay, So we're going to take a look at some examples of actually sketching some of these functions, okay? And one of the things that you're going to want to do, especially here at the beginning, is write down what's happening, okay? So we're identifying our parent function, and for right now we'll sketch the parent function and then sketch the variation of that parent function. But then we'll write down what actually is changing, and then we'll sketch it, okay? So our parent function for a quadratic x squared, f of x equals x squared, where's the vertex for this parabola? It's at 0, 0. And then what are some points?
1, 1.
1, 1.
2, 4.
2, 4.
3, 9.
3, 9. Okay. Go to the negative 1, 1, negative 2, 4, negative 3, 9. And we have our parabola. Okay. You guys should be able to graph the parent functions really, really easily. The better you know those, the easier the rest of this will be. Okay? So now we have to look at this. We're going to take negative 0.75 times f of x, which ends up being negative 0.75 x squared. So someone tell me one thing that's happening here.
It's a reflection.
Okay? It's a reflection across.
Y. What's the question? That's the x.
It's a reflection across the x-axis. Alright? So we're going to reflect across the x-axis. Okay? Eddie?
Vertical shrink by 0.75.
Good. There's also this vertical shrink. All right. So as we go to sketch this, what we have to do with each point is we need to identify where it would have been on the parent function and then what these transformations are going to do to that point. Okay? Now, if I'm at the origin, what will happen to that point?
It's consistent. The origin point's consistent.
It's going to stay the same, yeah. And unless you have some sort of a shift, the origin point will always stay the same. Okay? So now, let's think about our point 1, 1. Instead of 1, 1, it's going to get reflected across the x-axis, which would put it down at 1, negative 1, right? But then that y-coordinate is multiplied by a 0.75. So where does that point end up?
Would be 1. Negative 1.75.
Okay, 1, negative 0.75. Okay? So notice it's only 3/4 as far down as this one was up. Okay?
The next point would be 2, negative 3.
Okay, and here we have, it was 2, 4. If we reflect it, it's at 2, negative 4, and then 3/4 of negative 4 is negative 3. Good. Okay, so we have 2, negative 3. See how I'm working each point to find out where it would be now. Okay? Then we head to point 3, 9. So that's going to be negative 3/4 of 9, right? So
Negative 6.75.
there we are, negative 6.75. And then of course we can reflect those points using the symmetry we know exists here. So we have negative 1, negative 0.75, negative 2, negative 3, and negative 3, negative 6.75. And now we can draw our transformed parabola. Okay? And you'll see how this one isn't a real big shrink, okay? Is a real drastic shrink, I should say. But it does end up being a little bit more spread out, a little more stretched out because we've compressed it, okay? Any questions on that one?
I was only gonna question big shrink.
Big shrink? Yeah. All right. Our cubic parent function, Alexi. Yes.
I've been looking at what values make the graphs shrink or stretch. Weren't like stretching it horizontally shrink it vertically and vice versa?
There is a relationship, and I just kind of wonder when this is going to come up, but that's okay. Because it's kind of can play with your mind a little bit if you think about it too hard. My thing would be go for the obvious. All right. Here I have 3x cubed. Okay. If I wanted to, I could get the same thing if I wrote it as the cube root of 3x cubed. Would you all agree that that equals 3x cubed? Because if I cube the cube root of 3, I get 3, right? So, this is a stretch vertically 3 times as tall. The end result is that it will be compressed to 1 over the cube root of 3 as wide. Okay? But that's where I say go for the obvious. Here it's just 3 times the x cubed. It's a vertical stretch. Alright? This one up here, okay, a 1/3 x that's then cubed. That's the same value as 1/27 x cubed. So when I make it 3 times as wide, it ends up being 1/27 as tall. So yes, there is a relationship between the horizontal and vertical stretching and shrinking. Okay? So my thing to you would be go for the obvious. Okay?
So will you ever ask us how to look at a graph and then identify like what's going, like what kind of shrink, stretch, or like?
Yeah, and as long as you communicate accurately, like if you looked at the graph that was 3 times as wide,
Yeah.
and you said it was 1/27 as tall, okay, that works. All right, but if I give you the actual equation, just go for the obvious answer. Don't try to do any kind of manipulation or whatever to work it out. Okay. But to answer your question, the more you compress it vertically, it is going to naturally spread out wider. And the more you stretch it vertically, it is going to narrow. Okay? So. Alright, good question though. Thinking. Alright, so here we go. Our cubic parent function, f of x equals x cubed. Someone give me some points.
0, 0, 1, 1, 2, 8.
Alright, 0, 0, 1, 1, 2, 8. On this side, how about negative 1, negative 1, negative 2, negative 8, okay? So there is our cubic parent function. And then here, g of x is f of x plus 2, or x plus 2 quantity cubed. So let's see what's happening here.
It's being translated to the left 2.
Very good. It's to the left 2 units. Okay? Remember, the horizontal shifting or translation is the opposite of what you think it might be. Okay? The tendency is to want to go to the right, but it's horizontal. It's to the left. Okay? If you think about it again in terms of movement, like I mentioned yesterday, we're going to get up here to 0 2 units faster because we're adding 2 to it. So instead of getting to axis at 0, 0, we're going to get to it 2 units sooner at -2, 0. Okay? So that whole thing is getting shifted over here 2 units. Instead of getting up to 1 when x is 1, I'm getting to 1 when x is still a -1. And I'm getting up to 8 when x is 0. Okay? So, here we have our shifted parent function. Okay? Notice, same thing, it just got shifted over. Any questions about that one? Alright. Our radical function. Our radical function. Did you guys have this one sketched on your parent function handout? Okay. There's a 1 in here that we don't, so. Alright, so for this one, our parent function, first of all, what's our domain?
0 to
Yeah, 0 to infinity. Okay, greater than or equal to 0. So we start at 0, 0, then we're at 1, 1, and then square root of 2 is 1.414, so I don't feel like graphing that. Let's go with perfect squares. So 4, 2, and then 9, 3, right? So there is our radical function. Okay? So now we look over here. G of x is the square root of 3x. So what's that 3 going to do? Horizontal shrink. So what's its width going to, what's going to happen to how wide it is?
1/3 as well.
It's 1/3 as wide, okay? Okay, it's 1/3 as wide. Okay? Or in other words, all of your x coordinates are going to be divided by 3. Alright, so we're still going to hit 0, 0, but instead of 1, 1, we're going to be at 1/3, 1. Okay? So here's 1/3, 1. And instead of 4, 2, we're going to be at we're not doing anything on the calculator right now, so you guys can look up here. Or on the computer right now. Okay. Instead of 4, 2, where are we at?
1 1/3.
Yeah, 4/3 or 1 1/3, 2. Okay? And then instead of 9, 3, we're at 3, 3. Okay? So here is our shrunken radical function. Okay, or compressed radical function. Okay? So, guys, for each one of these, you need to at least be picturing this in your mind. If you want to sketch it lightly, you know, if you have to sketch one of these on a quiz or something, if you want to sketch it lightly, and then, so that helps you see what the new one ought to be, you're welcome to do that, okay? But you need to at least see it and know the points that you're dealing with in your mind, and then you can modify each point individually, alright? When you are sketching these, I want to see actual points labeled, alright? I don't want you to say, well, it's going to be something like this, okay? That's not good enough. We want to make sure that we're accurate, okay? So even if you're sketching it by hand and you don't have a graph, label points. Okay, if you have a graph, label the points and actually put the points where they're supposed to be. Sometimes I'll have people, you know, labeling stuff and it's nowhere near, you know, okay, this is the point, you know, 3/8 or something, and it's nowhere near where it's actually supposed to be. Right? Just be as accurate as possible. Yeah.
I get the whole 1/3 thing. I don't get how you got the points.
Think about your x coordinates. It's going to be 1/3 as wide. So this was the point, and maybe as wide isn't as a great thing. Maybe instead of as wide, you could say 1/3 as far from the y-axis. Okay, so instead of being here 1 unit away y-axis when we hit 1, we're only 1/3 of a unit away from the y-axis when we hit 1. Okay, and instead of being 4 units away when we hit 2, we're only 1 1/3 units away when we get up to 2. Okay, so just you can, if you know what this is, that inverse relationship, you can then multiply all your x coordinates by that.
Can't you just plug in x's?
You can just plug in x's, yeah. Plug in a 1, and you get the square root of 3, so it's 1 and 1.7. If you want to plug in a 2, square root of 6,
Oh, we can
2
do
point something.
Yeah, but that's the difference
Can.
between looking at it as a horizontal versus a vertical. Looking at it this way is truly looking at it as a horizontal. If you just plug in points to try to get coordinates, you can do that, it'll give you the shape. But this is really like making that recognition that look at the difference between those two functions, between f of x and g of x. What you see different between the two is the 3 under the radical, right?
Yeah.
So that 3 under the radical is really changing your input to the function. So what you're doing is you're saying for every y value that you get, how is x different? As opposed to, for the same x's, what y's do you get? That's what you would approach a vertical dilation.
Yeah.
I don't know if that makes sense or not.
Oh, yeah.
It's kind of a matter of perspective. It's kind of like what I was saying before,
It's not
where
the same, but
you could write this as a vertical. It's a vertical stretch by root 3. This is the same as this. Okay, it's just you don't have to try to work around a little bit, you know. So, all right. Absolute value. This is one that you're familiar with. Okay, absolute value function. Go ahead and try this one on your own. Identify your parent function, and you can do it on the same graph if you want. And then identify what transformations are taking place, and see if you can sketch it. like to put up our final answer? While some others finish. Is anyone done and want to put up their results? Let's do. All right.
I don't know if I got right, but. Should I do both or just that?
You could just do the variation.
Okay.
Too scared. Yeah. No, I got it.
Give you one.
I got it.
Doesn't give you.
You deserve applause, because you volunteer more than anybody else.
Good job.
You guys need to give him props, otherwise Mr. Hickson's gonna start calling on you.
Call me next.
You gotta volunteer, Mr. Hickson.
So you can speak with it.
All right. Good. Good. So this is what it all ends up looking like. You can see it's reflected across the x. All right, it's reflected across the x-axis because of this negative. All right, and then also the two doubles all of your y coordinates. All right, it's stretched vertically because instead of a 1, 1. It got stretched to be 2. Okay, instead of a 2, 2, now it's stretched to be 4. Okay? Now, one of the questions that came up yesterday was, should we, or not yesterday, last period, was should we reflect it first or should we stretch it first? And the fact is, it doesn't matter. Okay? It really doesn't matter. And in fact, even with shifts, as long as you're careful about how you do it, it doesn't matter what order you do things in. Okay? We'll see that actually with our next one. Okay? But does anyone have any questions about how Evan got this? Notice he did label some points, alright? You don't have to label the origin, that one's obvious, but label some points. Alright, so our next one deals with a parent function that we actually didn't put on our sheet yet. So if you want to get out your sheet of parent functions, we can add this one to it. And this is the reciprocal function. Okay? The reciprocal function. 1 over x. Now, the reciprocal function, obviously the domain is what? All real numbers except for 0. So you'll notice I put a dotted line going up and down on the y-axis here. That's because there's an asymptote there at 0. There's also a horizontal asymptote because since we have 1 over something, no matter what I plug in, it's never going to equal 0. Alright, it might get really, really small if I put a huge number in for x, but it's never actually going to equal 0. So there's also this horizontal asymptote there. Okay? Now, I'm going to actually go by halves. This will write for me. There we go. Just so we can see this easier. So there's 1. Okay? And let's find a couple of points, because you guys know what a function does when there's an asymptote, right? It approaches it, and it gets closer, but it never crosses. So, let's think about this. When x is 1, our function equals 1. So we know that there's a point right here at 1, 1. Once we identify that point, then it's just a matter of following the behavior as it approaches the asymptote. Okay? So as we approach this vertical asymptote, it's going to approach it but never cross. And then it's going to do the same thing here for the horizontal asymptote. Okay? But then we say, okay, well our domain was x can't be 0, but what happens if x is negative? All right? If x is a negative 1, we're at negative 1. So negative 1, negative 1. And then again, let's just follow the behavior as we approach the asymptotes. Okay, we're going to approach this horizontal one from the bottom. We're going to approach this vertical one from the left side. And there we have our reciprocal function.
So what the domain is like bracket 0, comma, how do we write that was the right difference?
Basically, for your domain, just put x does not equal 0. If we were doing an interval, you'd have to do like negative infinity up to 0, union 0 to positive infinity. But that's a whole lot easier. So, yes. All right, so now we have this situation here. We have our variation on this function, f of x minus 3 plus 4. Or in other words, 4 plus 1 over x minus 3. If you want to write it like this. Okay.
So it means moving to the right 3, then a 4.
Okay, good. So we have shifts going on here. Notice we're subtracting 3 from the x. That's going to give us a shift to the right 3. Okay? And then this is the reciprocal part, and then we're adding 4 to that whole thing. We're adding 4 to the whole function. That's what gives us the vertical shift. So we're moving which direction 4? Up, okay? Up 4. Now, be careful with this one, because the asymptotes move as well. And I'm actually going to move this over. Oh, we'll keep those two. All right, so everything on the graph is going to shift over 3 to the right and up 4. So where my origin was, here's 1, 2, 3 to the right, and 1, 2, 3, 4 up. Where the origin was is going to be there, and I like to put a little, crosshair there so I know that that's where that was. Okay? So now I'm going to draw my asymptotes again. But now instead of the y-axis being an asymptote, the line y equals 3, or I'm sorry, x equals 3 is an asymptote. And instead of the x-axis being an asymptote, the line y equals 4 is going to be an asymptote.
Like, why would that be the origin? And point to go, like,
It's not an origin, it's where the center of this graph here
Yeah. Oh.
is now going to be the center of our shifted graph. Okay? Just go away. Oh, that's right, I forgot I could move it. So now, think with me here. We had the point 1, 1. So I'm going to move from my shifted origin over 1 and up 1, and there's that new point. Okay? And if you think about it, 1, 1, if I move 1, 1 to the right 3, I'm over 1, 2, 3, and then I move it up 4, 1, 2, 3, 4, There we go. Okay? So now, this top part of my graph looks like this. And I shouldn't hit my asymptote. Okay? So there we have the top half of our graph. Then this point, -1, -1, also gets shifted over 1, 2, 3. Try that again. We were at -1, -1. It gets shifted over 1, 2, 3, and up 1, 2, 3, 4. Notice it's to the left and down 1 from where my shifted origin was. Okay? So there's that point. And I've got it. Okay? Now I am going to label these points. This is going to be the point 4, 5. And this will be the point 2, 3. Okay? So does everyone understand how we can move that around? That one's a little bit tricky because it doesn't actually hit the origin. So you kind of have to think of, all right, if the origin's moving over here, then everything else is moving the same. Okay? All right, now, I want to take some time here to let you guys work a little bit together on these on your own. Okay, we're going to take about 15 minutes just to break up, and I want you to work through some of these. Some of you may have done them because they were on the Sunday Post. If you already did what was here, then I want you to practice actually doing the sketches. Okay? If you haven't done any of this yet, what I want you to do and get with a partner on is taking a look at these graphs and notice the directions here. Identify the parent function. Okay? So write down what is the parent function, and we're calling that f. Write that down. Is f of x x squared? Is f of x radical x? Is f of x the absolute value of x? What is f of x in this case? Then describe the transformation. So that's what we were doing right here. We're going up 4 and to the right 3. Or you can say it's stretched vertically 3 times as tall or something like that. And then this last part says use function notation to write g in terms of the parent function f. This is what we saw here. It's -2 times the parent function. Okay? Here it's f of x minus 3 plus 4. Alright, so this is what that last part is asking you to do. Okay? So, like I said, I want to take the last 15, or not the last 15, the next 15 minutes or so here to let you guys work together just so you can get the hang of these. Alright? So, let's go.